So the point is, the claim we're trying to prove is that every integer is even or odd. Gotta be one of them. The formal statement being, for all n in z, and even or n odd. Not that hard. Not that hard to state, at least I should say. Let's start talking about how you'd actually prove this. Aside. So what this really comes down to, it's kind of like what we were talking about before, right? All we really have to show to prove this is that if n is not even, then n's odd. Because note, if n even, then n even or n odd, so it works, right? So we really have to show that if n not even, n must be odd. And we could do this the other way around, by the way. We could note that, hey, note like if n's odd, then n's got to be even or odd, so that works out. But if n's not odd, it needs to be even. Either way, we either need to show that if n's not even, it's odd, or if n's not odd, it's even. Yeah. So let's go about this. Now, first of all, you might be asking yourself, okay, wait a minute. So I'm trying to show here that if n's not even, it must be odd. So I'm trying to show that for all n and z, like this second statement here, is that for all n and z, not n even implies n is odd. You might notice, hey, we're in the contrapositive contradiction section. So, hey, we have an if then, let's try contradiction. Maybe that'll make it easier. But if we do that, we'll actually just get n not odd implies n even, which is basically just as hard. So contradiction is not going to give us much here. Or sorry, contrapositive is not going to give us much. Contradiction, here's exactly why I want to do this example. You can kind of use indirect proofs as tiny pieces of a larger whole. So your whole proof doesn't have to be proof by contradiction, but one piece of your proof could be a tiny little proof by contradiction. You're going to see that in a second. But for now, let's get going with this. How to show that if n's not even, n must be odd. So let's assume n not even. What's this mean? Well, n even means there exists a k such that n equals 2k. N not even must mean for all k in the integers, n does not equal 2k. Or another way to put it is 2 does not divide n. All right. But let's look at this. Let's get some colors up in here. Let's look at a number line. And notice that evens are in red here, right? evens are the reds. If you take any odd number, like 3, how far away is it from an even number?
It's 1 away.
It's got to be 1 away, right? Every even number is within 2 of another even number. So if you're not even, the most you can be is within 1 of an even number, right? They're actually within 1 on both sides. But kind of the one we care about more is the one below it. So notice that 3 equals 2 plus 1. It's an even number plus 1. And we care about that because that means it's 2 times 1 plus 1, so it's odd by definition. 5 is 4 plus 1. 1 plus an even number, that's going to be 2 times 2 plus 1. So kind of the thing to notice is that every odd number, that everything that's not even has to be 1 bigger than an even number, just because of the way the evens are so close to each other. The evens are all spaced by 2. The question is, though, how do we show that? Right? And that's where it gets difficult. But let's think about this. Yeah, think about this. Because what we really need to do is we need to take an arbitrary, not even number. So n's an arbitrary, not even number. And we need to show that there must exist some k star need to show there must exist some k star in Z such that n equals 2k star plus 1. And here is the clever bit. Here's how I'm going to do it. We can think about it forever, but here's a really interesting thing to look at. And that is, let's look at the set of all k's in the integers such that 2k is less than or equal to n. Why do we care about this? Well, if we draw the number line again, we look at that and we make like a 3 be our n, then our s in this case, let's think about it, right? Like we could do, so we're looking for all the k's in Z where 2k is less than or equal to n. So let's look at the 2k's, right? The 2k's are just the even numbers. So this is a 2k that's less than or equal to n. This is a 2k less than or equal to n. This is a 2k less than or equal to n. This is a 2k less than or equal to n, right? And all of these have k's associated with it. Here, if 2 equals 2k, k equals 1, k equals 0, k equals -1, k equals -2. The point being that here we're just looking at all the possible k's where 2 times k is less than or equal to n. The reason we care about that is because the biggest number in this set will be the number that if you multiply it by 2, it's as close to n as you can get. As we just talked about, that difference should be 1. So notice here, right? The biggest k that works is k equals 1, because that gets you to 2. If you try to use k equals 2, you get 2 times k, which is 2 times 2 is 4, bigger than our n, which is 3. So the biggest k that you can multiply by 2, and it'd be less than or equal to n, is k equals 1. But then notice that 2 times 1 is 2, plus 1 equals 3. The point is, the max k in here times 2 plus 1 should be in. How are you feeling? Isn't making any sense? All I'm saying is, let's try to find the biggest even number less than n. That's all this is. Let's try to find the biggest even number less than n. Or really, the k that leads to it. The biggest even number less than n. And what we want to show is that if you add 1 to the biggest even number less than n, you get n. Another way to put this is want to show the biggest 2k less than n, otherwise known as biggest even less than n plus 1 is n. How are you feeling about that? Does that idea make sense? That if we show the biggest even less than n plus 1 is in fact n, well then we've just found we just show that n's odd, because being odd and even being even plus 1 basically. Okay, well, this is making sense. So the point then is that, let's look at this. Let's define k star to be the max of S. So that just means the biggest number in S. And now our goal is to show that k star, or 2, so now I want to show two k star plus 1 equals n. Now here's how I'm going to do that. I'm going to do that by contradiction. So another way to look at this is this implies, this is the same exact thing as saying that n minus 2k star equals 1. Let's prove this by contradiction. So this is what I'm talking about. This little claim right here, this little claim is what we're going to use a contradiction proof on. So let's assume the opposite. Assume that n minus 2k star does not equal 1. Thus, if n minus 2k star does not equal 1, what does it have to be? Like, for example, if a does not equal 1, what does a have to be? What can we say about it in relation to 1? I give you a hint, there's two things it could be.
It has to be odd then, right?
Well, just using this fact that A is not equal, like forget about all this. Let's just look at this. Just using the fact that A is not equal to 1, like the opposite of being equal to 1.
Not equal to 1?
What do you say?
Or it is equal to 1? I guess like the opposite, it is equal to 1 or it is not equal to 1. That's the only two things.
Oh, sorry. Yes, so the opposite of being equal to 1 is that it's not equal to 1, obviously. But what that means is, think about this, right? Like, you know how toddlers go, like, how old are you? I'm this many. Like, if you're not this many, if you're not 4 years old, what are your options for ages?
Everything else?
Everything else. You're either older than 4 or younger than 4. Right? If A doesn't equal 1 and A is an integer, this is the same thing as A being less than 1, or since it's an integer, we can say less than or equal to 0, or A is greater than or equal to 2. Does that make sense? Like, and same deal with if A doesn't equal 4, if you're not 4 years old, well, then you have to either be 3 or less, or you have to be 5 or more. That makes sense, right? I think that makes sense. The point being, since n minus 2k star is not equal to 1, and n minus 2k star is an integer, the reason integers matter is, of course, well, because like if A doesn't equal 1, but A is just a real number, it's not necessarily an integer, well, then you have to use greater than 1 or A is less than 1. We can't say that it's greater than or equal to 2 because, for example, 1.5 would work. That would be a number that's not equal to 1. Yeah. So, thus we have that n minus 2k star is greater than or equal to 2, or n minus 2k star is less than or equal to 0. Let's disprove both of these independently or individually. If we prove this can't happen and this can't happen, and they both lead to contradictions, well, then this whole statement can't happen. And if this can't happen, that means n minus 2k star must in fact equal 1. That assumption, n minus 2k star does not equal 1, is false. It could not happen. So here's the idea. Let's look at this first. If this is true, that would mean that n is greater than or equal to 2 plus 2k star, right? Which means that n is greater than or equal to 2 times 1 plus k star. The whole proof, the key idea of the whole proof happens right here. What's the problem with this? Remember, we're trying to reach a contradiction. Assume this is for contradiction's sake that this happens. This happens, this or this happens. We're trying to show both of these avenues lead to contradictions. So why does this one's easy, this is going to be easier, this one's the hard one. So if we have this, we know we have this. Why is this a contradiction?
Is it our set?
Is what?
Is it our set?
It definitely has to do with the set, Benet. Exactly. What about the set? Oh, you got it.
We say that 2k is less than or equal to n, but then here we're saying that n is greater than or equal to 2 times 1 plus k. Am I crazy? Is that not a contradiction?
Yeah, so n is greater than or equal to 2 times 1 plus k. What's that mean about 1 plus k? Or 1 plus k star?
It's even?
We don't know it's even. Can someone help him out? if n is greater than or equal to 2 times 1 plus k star, 2 times this number, based on s, what do we know about 1 plus k star?
Not even? I'm confused.
No idea if k, like here, k star is the maximum of this. We have no idea if k star is even odd. We don't really care. What is s? S is instead of all integers, instead of all numbers in the integers, that you can multiply by 2, and it'll be less than or equal to n. Well, 1 plus k star is an integer that you can multiply by 2, and it's less than or equal to n.
Is it that we have like 2k is less than or equal to n, but we also have 2 times 1 plus k is less than or equal to n?
You're so close. You're so close. Here's the thing. We know that 2 times 1 plus k star is less than or equal to n. So 1 plus k star is an s. Right? Because s is just the set of all numbers you can multiply by 2 that's less than or equal to n. 1 plus k star, based on this assumption, is a number that is it's a number that you can multiply by 2 and it'll be less than or equal to n. So by definition of s, 1 plus k star is n s, right?
Does it get weirdly recursive? Is that the issue?
No, it's fine.
Okay.
But does that make sense? The whole we does this make sense that 1 plus k star is n s? Who doesn't see it? Makes sense, Benay? Herman, Justice, Afra, Safa?
I'm confused.
Same.
Same? I'm so glad you mentioned something. Good. This is, I mean, this is a confusing proof. But so S is the set of all integers that you can multiply by 2 and be less than or equal to n. So for example, let's make it real for a second. Like if n equals 5, right? Then S, which is the k and z, such that 2k is less than or equal to n, which is 5. And what's that going to be? Well, that's going to be, well, if k is negative, then it'll be 5. So it'll be like -2, -1, 0. Notice that -2 times 2 is -4, which is less than or equal to 5. -1, I really want dots here. -1 times 2 is -2, less than or equal to 5. 0 times 2 is 0, less than or equal to 5. 1 times 2 is 2, which is less than or equal to 5. 2 times 2 is 4, which is less than or equal to 5. 3 times 2 is 6. Oh, 6 is not less than or equal to 5. So this is what S says in this case. In the case where n equals 5, S is everything up to 2. All the integers up to 2, because after that, you can no longer multiply 2 by these integers and get something less than or equal to 5. So this is what S is. All numbers you multiply by 2, that gets you less than or equal to 5. Now, K star in this case, the K star we define to be the max of S. So in the case where n equals 5, k star is going to be what?
2.
2. Exactly, right? The max of the set. 2. But then, let's assume, we're under this assumption. Assume n minus 2k star, in this case, yeah. Assume that n minus 2k star, which is 2, is greater than or equal to 2. Well, that would mean that n is greater than or equal to 2 plus 2 times 2, which equals 2 times 2 plus 1, which equals 2 times 3. The point is, this would mean n, by the way, equals 3 here, or 5. So when n's an actual number, we can see, oh, obviously, 5 is not greater than or equal to 6, right? And since 5 is not greater than or equal to 6, this assumption must be wrong. This assumption right here. N minus 2k star is greater than or equal to 2. In our case, that's saying n minus 2k star greater than or equal to 2. That's saying that 5 minus 2 times 2 is going to equal to 2, which would be saying that 5 is greater than or equal to 2 times 3 based on the math we just did, adding the 2 times 2 to that side. And this is obviously not true. 5 is not greater than or equal to 6. So our n minus 2k star can't be greater than or equal to 2. But with integers, with actual integers, it just doesn't really matter much. But that actual integers, because obviously this is true, we'll move on. But over here, these aren't just like actual numbers we can look at. Here we can say, oh, 5 is definitely not bigger than or equal to 6, so this is wrong, therefore this assumption's wrong. Here it's not so obvious. Like, why is it that n can't be greater than or equal to 2 times 1 plus k star? Not so obvious that that's false. But look at this. In this case, if 5 was greater than or equal to 2 times 3 star, this means that 3 is an s by definition, right? The definition of being an s is you're an integer that you can multiply by 2 and be less than or equal to 5. Well, 3 is an integer, you multiply by 2 and be less than or equal to 5. So this means 3 is an s. But we know that 3 is not an s because 2 was the biggest number in s. This is a contradiction. If we assume this is true, then we get that 5 is greater than or equal to 2 times 3, which implies 3 is an s. But we know 3 can't be an s, therefore our assumption must be wrong because it logically led to something that was false. Does this help?
So, quick question.
Yeah.
For our actual proof on the left side, are we now able to prove that 1 plus k should not be an s?
Exactly. So for our proof on the left side, right, the analogous thing to do, right, this shows right here that by definition 1 plus k star is an s because it's a number you can multiply by 2, make something less than or equal to n. But why does this contradict? Like, what's the contradiction here? What's k star? It's not rhetorical. Like, what's k star defined to be?
Should be the max value, so we shouldn't be able to add another one to it, right?
Exactly. K star, yes, exactly, Renee, yes. K star is the maximum element of S. That's how it's defined. It's just, we know there's going to be one, defined to be that. In this case, it was 2. 1 plus k star is going to be bigger than k star. So if it was in S, that would mean that k star is not the max, but 1 plus k star is. The point is, this can't happen It's contradiction since K star is the max in S. So,
I have a quick question.
yeah, please, Herman.
So 1 plus k star, so if that's the max, let's say it's 2, which then becomes 3, which means
Yeah.
3 is the max. And can we plug it back in and say that 3 plus 1 would be 4, and then we could just keep going forever? So there's also kind of another weird
That's the crux
contradiction.
of the exact problem, right? That's another way you can look at it, right? Is that kind of yeah. I mean that well, it kind of stops because we assume K star is the max. And since K star is the max, if this assumption were true, 1 plus K star would also be an S. Under this assumption, 1 plus K star is also an S. But we know that can't happen because K star is the max. And 1 plus K star would be bigger, so it just can't be an S. So the contradiction there. But you're right that if you think about like, oh, okay, well, if this is wrong, then 1 plus K star, like if this assumption was true, like it's kind of like we define this to be true. So this is like a fact. This is a fixed point. This is the assumption we're trying out. So kind of, Benet. So this is kind of an assumption we're trying out. Like, let's just try out, see if this is true, what happens, right? Well, if this is true, you get a contradiction. You get that K star wasn't actually the max. But if we kind of look at it the other way, if we consider this to be a fact, well, then the problem is that you're right, that if this is a fact, if you were to say, oh, well, actually K star wasn't actually the max, K star plus 1 is, well, you plug that back in, and then K star plus 1 is actually the max. K star plus 1, it will be an infinite problem, and that's another reason that's kind of the exact problem, is the fact that K star is the max. You can't keep adding 1 to it. It kind of depends how you look at it, but you're totally right that that's an issue. If you look at it a different way, it's kind of confusing. I think it's easier to look at it as K star is the max. K star is the max. That's a fact. So 1 plus K star can't be an S.
Yeah, both make sense. It's just kind of cool. Just know.
Good. Yeah, no, it is kind of cool. Yeah. So this is why this is our contradiction. This can't be true. The difference between n and K star must be greater than or equal, cannot be greater than or equal to 2. So this is false. This can't happen. But maybe this happens. Let's look at the problem with this. If we assume this, well, that means that n is less than or equal to 2K star. But remember, K star is in S. So what do we know about 2K star? Every element of S, if you multiply by 2, what do you know? Based on this definition of S. Remember, S is all the integers, such that if you multiply by 2, it's less than or equal to n. K star is in S. It's an integer in S. So if you multiply it by 2, what should happen?
It should be less than or equal to n.
Should be less than or equal to n. So we should get this 2. And this is since K star is in n. What's the problem here? The problem here is that 2K star is less than or equal to n. So if n is bigger than or equal to 2K star, and n is less than or equal to 2K star, the only option is that n equals 2K star. But then that means that 2 divides n. But at the very top, we assume that 2 does not divide in. This can't be true. Contradicts assumption that n contradicts that n is not even. Meaning this assumption right here is also not true. So we've shown that n minus 2k star cannot possibly be bigger than or equal to 2. And we showed that n minus 2k star, the difference between n 2k star can't possibly be bigger than or equal to 2. And it cannot possibly be less than or equal to 0. Both lead to contradictions. Meaning n minus 2k star cannot not equal 1, meaning n minus 2k star must equal 1. N minus 2k star must equal 1. And what's that mean? That means n equals 2k star plus 1, meaning n is I. So the point is, if you assume that n is not even, well then let's just look at the even number closest to n, the biggest even number less than n. The difference between n and that even number can't be bigger than or equal to 2. Otherwise, there would be a bigger even number in between. And the difference between n and that even number can't be less than or equal to 0. Otherwise, that would mean that if the difference between n and the biggest even number less than n is 0, that means n is that even number, meaning n is even, which can't be true. Therefore, the only option is for n to be an odd number. I did not mean to spend the whole class on this. And to save time, I'm not going to actually write the proof out right now, the formal proof, but it goes exactly like this. What I'll do is I'll write it out on a piece of paper, and then I'll put it on Canvas. I'll put it in the page for this lecture, like for section 4.7 day 3 page. But it goes just like this. But let's get to the most beautiful proof in math, because I have been, which is a lot easier than this actually, because I've been peddling that for days now. So that is the really complicated way to prove that evens and odds are opposites of each other. The most simple statement in the world actually took all that to prove, but we can do it. That proof's not that important. That proof is like the way harder than anything you ever see on a test or anything like that. I just hope that you guys can see the mechanics of like contradiction being used here and there.